The article that I'll be talking about is called Plant Leaf Classification Using Probabilistic Integration of Shape, Texture, and Margin Features. This article was originally written by Charles Maller, James Cope, and James Orwell. My name is Ryan Demagard, and I'm going to be reviewing this article. So the first question that you might have is, why would we care about leaf classification? Well, plant species are not only vast in number, but also in their usage. Estimates of the number of species of flowering plants range from 220,000 to 420,000, according to R.W. Scotland and A.H. Wortley. Automatic recognition of plants is useful for a variety of industries, such as agriculture and medicine, reduction of chemical wastage during crop spraying, and also for species identification and preservation. Now imagine you're going to the doctor and they give you medicine, but it's the incorrect one. That could cause some serious medical problems. Also, when trying to track and preserve species, if you identify the plant incorrectly, you might be wasting a lot of efforts trying to save a species that's not truly endangered. To determine which class the leaf belongs to, we're going to need to focus on a few features. The overall shape of the leaf, the fluctuation and intensity of pixels within a window, and a few detailed components about the perimeter. Firstly, we're going to take a look into the shape component of the leaf. We're going to use a centroid contour distance curve shape descriptor function. What this does is simply select a lot of points along the perimeter of the leaf and then connects the points. From these points, we can calculate the centroid of the leaf and determine its general shape. It then creates vectors from the centroid to each point along the perimeter of the leaf and then divides it by its length. This generates the normalized leaf shape, which allows us to ignore how zoomed in an image may be. We then compare the normalized leaf shape to the pre-existing trained database to determine which leaf classes it looks most similar to. Then we take a look at the texture features of the leaf. We first select 1024 small random windows and apply a Gabor filter. This filter is a combination of a Gaussian kernel and a function modulated by a sinusoidal plane wave. From these filtered images, we can then extract the average positive and negative pixel values within the window, the energy or intensity of the colors, and entropy. To extract the margin features of a leaf, a median filter must first be applied to the binary leaf image. We then acquire a smooth version of the leaf shape and select n evenly spaced out points. These points are then used to calculate the corresponding point on the original leaf outline. So in other words, we apply a noise-canceling filter to properly select the points along the perimeter of the original image. At this point, we then create a small window around each perimeter point. The first feature we look at is the magnitude. This is the sign difference between the filtered image and original image. The gradient, which represents the sign difference from one filtered perimeter point to the next, and the curvature, which represents the angle created between three consecutive points. For this article, the authors use an algorithm called KNN. For me, the easiest way to understand this algorithm is with an example. If you look at the graph, there are two classes, red dots representing basil and green dots representing oregano. If we let k equal 3, that means that we'll take into consideration the three closest points. If we're testing to see what class this star belongs to, then based on the KNN algorithm, we would get 3 votes for basil, and thus the algorithm would identify the star as basil. In most cases, k will be an odd number. This is to avoid having a tie in votes. Once all the features have been calculated, the classifiers are presented in a histogram. The vote for the shape feature is weighed heavily. KNN is implemented on all of the texture features per window. Since we have 1024 windows, 1024 votes are issued. The fine margin features also get a vote on which classifier it believes the image belongs to. Once all votes are made, the class with the most votes is our final decision. Using cross-validation, a 96% accuracy was obtained. Potential ways to improve the accuracy of the classifier discussed could include an increase in database size, improved image quality, or potentially using different types of filters when extracting features. The reason why MATLAB would be very useful throughout this classification process is because MATLAB is designed for image processing and could potentially extract the shape, texture, and margin features more accurately. Here are the sources that I used.